hopefully not be too stressed when I'm giving you this talk. Okay, so that's me. I'm head of discipline for simulation assessment, which is essentially anything to do with calculations and simulation for Assystem in the UK. And this is what I want to talk to you today. So basically introduce what the project was that we have recently completed, what its aims and scopes were, what system architecture we did. Most of the discussion is going to be based around a couple of examples of the sort of models that we have incorporated, these live digital twins, and I'll talk in a second about what that means. Touch on the potential benefits and then a few conclusions. Okay, so up front, what we were trying to achieve. Well, first of all, it was a project that was funded by the government, by the SBRI, Small Business Research Initiative, I believe it stands for, in conjunction with the United Kingdom Atomic Energy Authority, as part of a project to try and accelerate fusion plant design, going forward for that sector. And what we tried to do, and what we hopefully I will show you that we did achieve, is that basically it is possible, it is feasible to link structural integrity models, the sort of calculations, very detailed calculations that are done to justify the integrity of nuclear plant, to actually a live data stream from an operating plant. Okay, now the first thing I would say is I don't have a live operating fusion power plant. So a lot of all of the data that we've used here was entirely synthetic in origin, but the kind of process I'm going to show you today was what it would be if you were actually measuring real data off a real plant. We wanted to make sure that we could link a wide range of simulation models, and that's quite important because the sort of calculation models that are used to justify a plant, there's a huge range. There's an enormous quantity of suppliers and designers and manufacturers, and also models associated with maintenance and inspection and costing and all sorts of things. And there's just a massive range. So we wanted to make sure that essentially we could tap into, or demonstrate that we could tap into, a wide range of these sorts of models. And that's quite important, rather than trying to force fit them to one particular software vendor. That's quite important. We also wanted to make sure that we could scale, to demonstrate that we could scale the architecture. So we could start off with literally just a single model and be able to essentially add additional ones to it. And finally, on this slide, to make sure that we weren't essentially designing another white elephant that sits in glorious isolation and doesn't talk to anything else. So we made sure that we didn't do that. And one of the systems that we tapped into was a simulation process and data management system that UK AEA use. So that means that we could essentially continuously, for the life of the plant, start to upload simulation data to their system if they wanted to do that. And obviously it was a feasibility study, so I wasn't throwing gigabytes every few minutes at their servers, but in principle it can be done. Okay, so why do we want to do this? Well, Assystem's background is really in power generation, traditionally in the fission power generation sector, but now as well in the fusion power generation. And one thing we do know is it's expensive. It's expensive to design, it's expensive to manufacture, and it's expensive to operate. Okay, just like any other power plant system is. Now, with nuclear specifically, but generally with all industries, you have something called the design basis life. Okay, so that is effectively the loading that you think that this part, component, system, subsystem will see through its anticipated life. Now, with the nuclear sector, especially in the fission side of things, that design basis is very conservative, as you would sort of hope it would be. The regulator expects that design basis forms a level of conservatism. There's conservatism elsewhere in terms of material capabilities and so on. Okay, so that's fine, and that's how you define the life of your plant. And in fission power, that goes into a set of reports, which is brought together to make a safety claim. And if the regulator approves that safety claim, then it goes into a site license, and away you go. Now, I guess the issue is that the really expensive bits in your power plant, the bits that maybe you can't inspect as well as you would like to, their life is defined by this worst case design basis loading assumption. And that generally defines the duration of your safety case that you've got, and there's periodic updates to that. But in reality, what the plant actually sees is potentially significantly less onerous than this worst case design basis that you've got. And the way it's done at the minute is this periodic update of the safety case often takes benefit from this difference between the worst case loading that you thought you were going to see and the less onerous case that you actually saw. And that can form the basis of life extension programs. And they're not cheap either. To stand those up from scratch, to do all those calculations all over again and update your safety case is not a trivial undertaking. And that, that isn't done very often. And what we're going to try and show here is that if you set these digital twins up in the way that I propose here at the beginning of your operating life, you've effectively got continuous life updates, information available to the operators of the plant, and if the regulators wish to see that, the regulators of the plant. How they use that, whether there's enough confidence to essentially update the safety case on the fly, that's a different matter, and we didn't address this here. But the point is, we can generate this data live constantly, rather than having to stand it up every, say, 10, 15 years, which is very expensive. Good news is that in these really expensive power plants that we've spoken about, we're generally swimming in digital models, simulations, calculations. There's a huge amount of work that goes in to underpin the design assessments of these sorts of plants in the first place. The better news is that effectively these models are fit for purpose. They underpin aspects of the safety case. These are models that you can trust the answers for. And the really good news is they've actually already been paid for. When you come to the end of the design phase, the designers of the plant have effectively already paid for these. And what happens currently is at this stage, you get to the end of your design assessment, these really expensive models that you know are good, that you've spent a lot of time and money creating, are effectively lost. They're archived, they're put away, and the operators don't see them. What we want to do is to carry on using them. So carry on being able to extract benefit from these models that we've spent a lot of time and money in creating. But rather than feeding them with a design basis, or indeed in addition to feeding them with a design basis, we can also feed them with the data that's coming off the actual plant by connecting them, and that's what makes them a digital twin. All this stuff up here is just a model. Okay, people tend to use the term digital twin to describe these things. In my opinion, it's just a calculation model, and they've been around for decades. It only becomes a twin when you've connected. So you've got to have two things to have a twin. You've got to have the model and the plant, and you've got to connect them. And that's the definition that we're going with here in Assystem. I think it's gaining traction. So what they can do is they can provide virtual gauges. Well, what do I mean by that? Well, you will have sensor instrumentation on the actual plant. If you use that sensor instrumentation on the data that's provided in the time history, push it through a digital twin, you can then start to extract a whole bunch of virtual gauges. In other words, calculations at specific points, maybe for regions that you can't actually instrument. You can't get inside a fusion reactor and start sticking thermocouples and strain gauges everywhere. Similarly, you can't do it in the reactor pressure vessel of a fission plant. They can also give you derived values that you can't actually measure. There isn't a fatiguometer that I can stick to a piece of metal that outputs fatigue usage. but my models can. So that can essentially start to provide these additional virtual gauges. And the point really is, if we can help enhance the life of the components, in other words, if we can start to quantify the difference between the design basis and its actual usage, then we can potentially add real value by extending maintenance periods, extending the overall life of the plant. And then that's starting to be commercially very useful for the operators. Okay, so how did we do it? The system that we'd used, and I would stress this was a small feasibility study, so this isn't necessarily the system that we would operate in practice. So we used a commercial off-the-shelf IoT platform, really just as a means by which we didn't have to code one up, essentially, and there's lots of these things around. It also had a small amount of data storage that we could essentially use that as our data historian as well. And we transferred information to and from that essentially over the internet using APIs. So effectively, we had some Python programs, one for each basically twin, that went off to that IoT platform, grabbed a chunk of data, say a couple of hours worth, brought it back, parsed it in the appropriate format, pushed it through the calculation models. Calculation models then were automatically post-processed. Specific outputs, or virtual gauges, if you like, were then extracted and pushed back up to that platform. And then the Python program went off and got the next hour's worth, and so on and so on. It just sat there running, ticking away 24/7. We could visualize the results on these whenever we wanted to. We could just dip in, and that's using a program called Panopticon. And the cool thing about using an IoT platform is that what they're really set up for is having functions and alerts and making data-driven decisions. So if something changes, then do this. And we made good use of that. So, for example, we could start to send text messages or SMS alerts or emails and such like when when a specific event had occurred, like, for example, a simulated earthquake. Okay. So graphically, this was the data stream coming off the actual plant. Now, as I say, this is an entirely synthetic data stream. So we had some other Python programs pretending to be a power station, just throwing data up onto SmartWorks. And there it was stored in time history. We had a bunch of programs that were going to the platform, grabbing some data, processing it, spitting the results out, all with a timestamp. So it was all sort of coordinated, and then just went round and round and round a loop on this forevermore. In the future, we'll probably do this fully up on the cloud rather than running this programs locally at Assystem, but that's where we were for this particular project. So in terms of the structure integrity models that we connected, there was a relatively small range. We'd picked some of the larger FE programs, so ANSYS and Abacus. We had some programs running. We had functional mockups connected. We connected commercial programs, in this particular case, Design Life. So that was going off and grabbing stress data and running it through a fatigue program to calculate fatigue usage. We connected to Excel, so this was constantly running Excel macros for crack growth in this particular case. And we also had connections, as I said, to UKAEA's SPDM program, which is called SimDB. So those are the connections that we made. Obviously, the connections to each one of these is somewhat unique to the requirements of each program. And creating these links is not to be underestimated. When we go to sort of containerization of this, it's going to get a bit easier. Okay, so a specific example then of one thing that we've done. So in this case, it was to do with a nozzle on a bit of pressure equipment. So we were feeding data to SmartWorks. In this case, it was a temperature, pressure, mass flow rate, and a neutron flux. Obviously, that's all synthetic. We then had an Abacus program that went into the SmartWorks database, grabbed I think it was about an hour's worth each time of temperatures, pressures, and mass flow rates, calculated heat transfer coefficients, did a thermal structural transient calculation to work out how the current state of stress and temperature in that part, and started to push back at specific key locations, temperatures, and a stress tensor. It's important to know we're not trying to push back in many gigabytes of Abacus results files into this. We're just looking at specific key points at the predetermined locations that the safety case has said that we would be concerned with. Say, for example, in the crotch corner or at a weld location. Okay. We had a second twin, which was running fatigue. So that was going in and grabbing that same temperatures and stress tensors, seeing how it varied through time, calculating damage and a remaining useful life, and putting that information at each one of these key locations back onto SmartWorks. We then had another model which was taking in the neutron flux and calculating what the current likely material toughness values were, and the thermal shifts, and putting that material toughness back onto SmartWorks again with the same timestamp. And finally, we had a fourth twin, which was essentially grabbing that temperature, stress tensors, through wall stress distributions and toughness, and doing a crack growth calculation. So it was when we had reversals in stress, we would have a reversal in something called a stress intensity factor, or SIF, and that increases the defect size that could exist somewhere in here, increases that defect size a little bit, and then we recalculate what our how close we are to having a problem with brittle fracture at that point. And the sort of data we were pushing back was reserve margin and what the current defect size actually was. So these are all sort of little Python programs or digital twins that were just ticking away, grabbing data, doing stuff, pushing data back, and just merrily going on their way, really. What I would say is that these particular models, because they were actually 2D axisymmetric models, they were running pretty quick. So I was not far short of real time. Obviously, as these models take longer to calculate, we're going to run a bit behind schedule. We're not really intending to have real-time results. I don't think we really need real-time results, and I very much doubt the regulator would allow us to make decisions based on that real-time information. So even if I'm, say, 6 months behind what the current fatigue usage is, that's still better than the current situation, which is a monolithic safety case that might have been written 10 years ago and has not been touched since. So as long as I'm closer than 10 years behind, then I'm kind of winning. Okay, so this is a vastly speeded up version of what comes through Panopticon. So on the top, this is two of the inputs, sort of pressure and a temperature. So we've got some color to this synthetic data. Every now and again, I'm pretending that some transient event has happened in the power plant. This middle row here, this is the predicted temperatures at a few key locations. Now, if we had some real thermocouples on the real plant, we could also predict what the temperatures would be at those real locations, and then we can compare them with what it's actually seeing and starting to get a real-time understanding of drift or error between the prediction and the actual result. And that's a big step forward, because that's effectively real-time validation of the calculation models. And at the bottom, we have essentially a stress tensor. It's 2D axisymmetric, so we've only got 4 values of how stresses at a particular point will change with time as a result of the changes to the input conditions. And it's effectively this that then is used by the fatigue program, for example, to calculate damage. So we can show that to the operators if they wish to see it, and they can dive in and drill down and see this. So this is effectively a fatigue life prediction of a particular location in the pressure vessel, and you can see how the total life of the plant essentially changes over time. So it starts off where it is. The life reduces a little bit because in that first few events there's quite a lot of movement on the data signal, so that's kind of creating damage, and then it kind of settles down a bit, and the predicted total life then increases, and we can compare between fleets. And this is another cool thing about IoT. If we start to pull in data from different plants, for example, say in a small modular reactor or a fusion fleet of power generations, we can start to feed all this information in and see the differences between the operation of different units at the same site, or indeed between different sites. Some plant might load follow, for example. It might start to shut itself down in periods of low demand, which is good for economics purposes, but maybe is not so good from a durability point of view, because you're starting to introduce a lot more startup and shutdown sequences, which can be quite damaging. So remember, I said in the bottom right-hand corner here, we were doing defect calculations in here. So this is essentially how those defect calculations go along. So the green line is our current defect size. So we would postulate that we had a 25 mil deep crack. That's just the way safety cases work. You have to assume that your structure is riddled with defects at just below the inspection capability of the NDT that you use. So if you've got some equipment that can detect a 25 mil crack and you find nothing, you have to assume there's a 24.99 millimeter crack everywhere. And then we have to grow that in our defect tolerance. So over time, that green line goes up as all these little stress sequences occur. And this is actually making the crack get bigger. Now, I've dramatically increased the crack growth rates because I didn't really want to wait 40 years to see this green line move. In reality, it would basically be a flat line and it would go up very slowly over time, but I've accelerated it here. So the green line is our current defect size as it gets bigger, and the red line is the maximum permitted defect size if, for example, at any stage we had a loss of coolant accident and we needed to inject cold water into this reactor to cool it. There is a limit to the defect size that can exist before we actually would start to worry about brittle fracture. So obviously the key point then is when the green line would pass the red line, because that's when we've run out of life on this particular part. And again, so this sort of level of data is there, and it's very detailed, and you can drill down to it, or we can essentially boil it down to just a single number of a fracture margin. And the operators could be sitting there and seeing these values alongside all their other values without realizing the complexity of the calculations that go into this. But nonetheless, when this number gets below 1, that's when we've run out of life, and we can extrapolate forwards in time based on the historical usage to say, well, you really need to be inspecting in 5 years' time, or you need to be replacing this part in 10 years' time, or whatever it might be. And again, this is dramatically different to the current safety case approach, because these numbers are based on what the plant has actually seen, not its worst case design basis that it was designed for. So another example, this is more of a seismic one. So we had a set of digital twins that effectively were taking in synthetic data from accelerometers that might be could easily be connected to some key equipment in a power plant that would be sitting there measuring basically nothing until an earthquake occurs. When that does happen, it triggers and it starts to throw its raw acceleration data onto SmartWorks, and that would be coming in at a very high rate, probably 500 hertz or something like that. We had another twin that essentially took that raw data, did some data conditioning for it, for checking for drift and things like this, and put that process data back onto SmartWorks. And then another twin which actually did the time domain dynamic seismic assessment. So it took that process data, ran through maybe the first second through, and pushed back stresses, plastic strains, forces, displacements, velocities, and accelerations, and then grabbed the next second and ran that through, and so on and so on. Okay, so why would we want to do this? Here's an example of an entirely synthetic earthquake that we've created, and this is a model of a cooling system. It's a public domain model, so I can show you this. But this is some, say, for example, some feed water that was going into a key part of a reactor plant, and therefore has to be seismically qualified. So we can then start to see how the displacements, how the forces in the various pipe hangers, which are seen here. We can see how they vary with time. We can see how the stresses at pretty much any location I would like vary with time, or the plastic strains, or the peak plastic strain, anywhere in the model or anywhere in that system. And all that information is there and exists and is pushed back up onto SmartWorks. And then we can start to interrogate that data. We can start to look at, in this particular case, how the pipe hanger forces vary with time for that specific earthquake that's just happened. Not the design basis one, not this horrifically big earthquake that the plant has been designed to, but the one that's just happened a few seconds ago. And we can start to compare forces, and we can use the logic built into the IoT platform to start to sentence whether or not this system basically has seen an earthquake that's within its design basis or that's without its design basis. So we can then start to decide whether we inspect that system or not. If we do decide to inspect that system, SmartWorks can point to the specific hanger, specific location that's seen this biggest forces, the one that's most likely to be damaged, and say, you need to be looking here first for that particular earthquake form that's just happened. So it's very bespoke and very unique. Okay, so that's just two of the examples. Just sort of wrap up now and talk about sort of some benefits and a few applications and conclusions. So the obvious one is for asset integrity or structural health monitoring and life extension, because we can provide additional information, these virtual gauges that you simply can't instrument. And they're often the things that affect your life. We can actually provide information about the sort of current state of damage compared with what it should be from its design basis, and that allows a schedule of inspection and replacement, and a direct comparison between what it was designed for and what it's actually seen so far. As you said, just showed with that earthquake example, we can get faster return to service by directing detailed and key inspections on the systems that were most likely to be affected by that specific earthquake that's just happened. And of course, if we could have multiple digital twins running in parallel, so I might decide for safety's sake, to run one model through with the actual accelerations that just occurred, and then another model through with that acceleration trace that was scaled up slightly, and yet maybe a third model where we'd assume that there was a bit of corrosion or thinning on some of the pipe work. Because you're not really limited other than by sort of software and hardware resources. I can have as many twins running in parallel as I want. I can then start to use some of these models to compare areas in my plant which I've got real data for, strain gauges, thermocouples and such like, and I can start to compare them with my predicted values at those same points to start to bring in model validation on the fly as we're going through. And again, that's not something that is possible at all with the current state of affairs. Normally, these models are done before the plant is actually built, and they're built to code, and the models are calculated and heavily verified, as you might hope, but never normally compared with the data that's coming off the actual plant when it's built. With this, you can do that. And finally, I don't need to be operating only on prior data. With a couple of clicks of the mouse, I can essentially clone some of these digital twins and throw the next 60 years of operating data at it. And I can try different what-if scenarios, for example, load following or base load. And I can get them to run ahead of time to see what effect that would have on damage. And then I can start to say, well, the load following plants are going to need greater inspection, and someone higher up can decide whether that cost of inspection is offset by the additional economics of load following. Data science, that's the big one that we want to go for, and at the minute we haven't really explored that at all, really. But we're going to have a historical data set sitting somewhere in a database of essentially inputs and outputs. And there's no reason at all why we can't have some physics-informed neural networks or artificial neural networks to try and join the dots and try and come up with an algorithmic equivalent that connects the inputs to the outputs. And if I can do that, then I don't need to run all these complicated ANSYS and Abacus models. I can just boil it down to an algorithm. And again, because these models are available, I don't need to only look at that historical data set. I can give these digital twin models to the artificial neural network and say, right, well, there you go. There's a gym for you. Ask this thing questions and it will give you answers. So you can be used to train these algorithmic models. Yeah, and as I said, the idea really would be to ultimately to try and not have to run things that take a long time. I'd like to run an algorithmic equivalent if I can. I did briefly mention something about uncertainty quantification when I mentioned about running scaled versions of those acceleration cases. Well, of course, I could do that from day one. I could run lots of different digital twins that maybe had slightly different heat transfer coefficient correlations. I could have different models that were running with slightly different material properties, strength, growth laws, even basic things like material modulus. I can have these things kind of running in parallel if there was enough sort of need to do that. This third point here about slotting in new models, easy enough to do, especially if it's containerized. And this last point here about models not being lost, it's a really trivial point, but the amount of times that I've been involved in life extension programs and I've tried to get hold of the original models that underpin the safety case, and everybody knows that they exist somewhere on a 8-inch floppy drive somewhere probably, but no one can find them and they're essentially lost. Here, they'll be running for the entire life of the plant in parallel. So it's a trivial point, but you can never actually lose your models, which is kind of cool, really. Final point is more on economics. So let's say that you had these models that essentially gave you a self-diagnosing plant and a self-safety case writing plant in extreme cases. If the operator decides that that's really going to be really good for them to extend their life, they may decide to pay a bit more to the designers of the plant to have that, and therefore some of the development costs for creating these models in the first place can be amortized not just across the capex, but also from over the opex over the life of the plant. And modern plants running out to 60, even 80 years, or potentially even more. So that's a big deal commercially. So where are we going to go next? Well, we want to do all of this, but actually do it on a real thing. So we're looking for partners to do that with. We've we've had quite a bit of interest from the new build side of things, but for anybody here listening who would like us to try this out on their kit, then please get in touch, because there's long-term operation stability and performance issues. This whole project probably only lasted 3 months end to end. So there will be issues associated with the usual things you get with data, like quantity, security, dropouts, stability, all that kind of stuff, and just get some practical knowledge of how this would actually work in the real plant. We definitely want to investigate data science much more than we have in those 3 months, and finally, increase the connections to a few other things, lots of other things. So MathCAD sheets, financial models, risk and safety models, PSAs, things like this on the safety case. That's something that we've that's uncharted territory for us at the moment. So that's what we've done. We've got an IoT backbone based on SmartWorks, to which we've connected models, quite a few different types. They're merrily calculating information which we are been able to visualize and been able to condense down to really simple metrics for the operators. We can use the IoT. The thing that IoT is good at is making decisions based on that data, and ultimately to try and get this into operation to make these plant a bit cheaper, and that obviously is going to help in the net zero push. And that is it. So Kevin, over to you.
No, thanks very much, Adam. Just for everybody on the call, if you have any questions, you can put your questions in the chat or in the Q&A. So I just got a couple of questions, Adam. First really was, you talked about major events within the power station or within the nuclear or fusion power station. Could you just expand on what sort of major events would typically be of concern to the operator?
Okay. Well, so there's two that I touched on. One was a seismic event, and there are nuclear plant based in Turkey and Akuyu, for example, and getting back online quickly after a seismic event is a big deal. It's millions of dollars a day in lost production. So if we had some digital twins that would assist in the walk down and inspection and the return to service of each individual plant, that component or system that needed it, if you get back online half a day earlier, then that's £500,000 minimum that you're generating. The other sort of major event I was talking about was in relation to defect tolerance. That red line and green line for the crack size, and that's when you're doing your defect tolerance, you have to assume that at any stage you could have essentially a plant finishing event where you have a major loss of coolant, and you have to demonstrate that your system will remain safe, it will remain intact, and we do that by doing these complicated crack growth and defect tolerance assessments, which is fundamentally what was behind those red and green lines earlier on. If that answers the question. I don't know whether it does, but
it does. Thank you. The other question I've got is there any restrictions with the sort of the data that can be collected and used within these models?
That's a really good question, actually. So certainly with fission plant, you basically won't really be able to get anywhere near the actual live control room. There's way too much security associated with that. But again, that's fine because I don't need the live data stream. What you can get is data from what's called the data historian. So everything that comes out of the sensors goes into the data historian and is sort of squirreled away. And because the operators aren't using that as live data, you can actually get to that. And we do get to that in some of our plant where we do similar sort of things in France. For equipment that doesn't carry the same level of sort of safety considerations that say fission plant does, and fusion's probably going to be that way. Fusion's probably not going to, well, isn't going to be regulated in the same way. Chances are we can either pull data directly from the sensors or from the data historians. With regards to the other aspect of data security is getting this out up onto the cloud and the associated, risks and cyber risks there. I personally think this is most likely to be, most of this is on premise, so inside the firewall, and what they're and essentially onto the corporate network of the fleet of operators. So it's unlikely to be cloud hosted, I think, but it remains to be determined.
Okay, we've got a couple of questions just come in. This is in two parts, really, this one. So
we'll just give us the first one first, then. I can't remember two things.
Yeah, I can't read two things either. Approximately how many fracture mechanics spreadsheets, FE models, etc., were connected up in the experiment in this piece of work?
In total, I probably had about 20 to 30 twins. Some, probably 5 or 6 of them were FE models. The rest were a combination of things like encode, functional mockups, Excel and things like this. So it's probably 20 or 30 in total. Okay. And the second part?
And how would you estimate the overall system coping with increased numbers of these when thinking about a full set of components on a live plant?
Yeah, well, that's a good question. The easy answer is I don't know yet, because we haven't really scaled it up. Now, we are thinking about that, and we've spec'd out some Azure platform where we're going to run all these, and they can be spun up and spun down as necessary. So it's sort of in a way completely scalable. But so I think the important bit of that question, the good bit of that question, is that where would you want to do this? And I would argue there's only any point in doing this on something that actually needs it, something that's actually going to add value, something that's life limiting and expensive. So, for example, on fission plant, you don't do defect tolerance on very many things at all. Actually, you do it on the bits where the FMECA, the failure modes and effect and criticality analysis, says bad things will happen. So you need to demonstrate that you are defect tolerant. So you probably wouldn't do it on, a bit of HVAC ducting, something that you could easily inspect, and if it failed, it didn't matter. You had a backup, and it was easily replaced and not that expensive. You wouldn't bother with any of this because it wouldn't add value. You would do it on the expensive stuff that was life limiting for the life of the plant. So actually, I suspect you wouldn't need hundreds and thousands of these things. You'd probably have, a couple of hundred at most, I would have thought.
Okay, Adam, we'll just round up now, just to say a big thank you very much from us all for sharing your work, and I hope everyone's enjoyed that.
Yeah, great, and thank you all for the people for turning up as well on a 7:15 on a cold Wednesday night when the football's on. So yeah, thank you for your time. Actually, I really appreciate it.